Uh, Good afternoon, everyone. My name is Jin Young Song. I'm an associate professor at UB Architecture Department. On behalf of the team UB and Alfred, thank you very much for organizing this event, and we are very happy to present our research project, the ceramic application of reconfigurable stack-interlock system. Our study is based on interdisciplinary collaboration. So Dan Vrana and myself worked as architects and fabricator, and also Jongmin Shim and Jiata Wu from UB Engineering Department worked as a structural engineer, providing the finite element analysis. We also closely collaborate with Jonathan Hook and Sean Murray from ceramic art program in Alfred University. So talented students from both schools contributed to this study significantly. And also Boston Valley provided valuable comments for this study. I think based on these diverse backgrounds and perspective on the material, this allowed us an opportunity to rethink the fundamental property of terracotta. So, which is fantastic for the longevity and like permanent use. On the other hand, we also acknowledge the shorter program life in the contemporary market dynamics and also temporary structures, what we call pavilions. And then more ephemeral urban space making is happening in many places. So we question ourselves that can terracotta respond to these two different timescales? So of course, the assembly mechanism matters, so that we learn from the traditional wood joinery. On the left, this is Otgari Tok joint from 14th century Korea. So that we know that this is not for the disassembly. However, we learn the simplicity and then kind of reversible structure based on putting the dowel in and out. So that if that's possible, we may change or contribute a bit of a perception of this material from the professional assembly for the skilled labor to more intimate use for everyone. And if we do that, if we try to make novel mechanism of the system of aggregation, we can also try the certain level of geometric freedom, so that beyond the modular and repetitive nature of the terracotta panel assembly, we can try to make a bit of a organic growth of using the unique stacking mechanism. So for this concern, we know that there are previous research about dry stacking, and also we kind of learned a lot from how the block design itself can be evolved to make the more performative aggregation system. So that our team is capable of doing this research. We have been interested in this topic, that these works are from our team, that we innovate the block design, and then it can aggregate in different way, so that we use the plastic, wood, concrete, and steel, and so on, so that all of these are based on unique interlock mechanism, and also everything can be disassembled pretty easily. So we're particularly interested in this system of aggregation, because we think that the future manufacturing and the construction system will integrate with the development of the robots and the swarm robotics, because construction sites, there are too many heterogeneous tasks, so that in terms of machine learning and then robot development, we can easily use the simplicity of stacking, so that, for example, robots can stack based on the simple action, so that in a way that how we innovate and develop the stacking mechanism will be very useful for imagining our future construction. So based on this kind of motivation, so that we designed the unique block. So this block has a bit of a unique geometry, allowing the jamming phenomenon by dowels. So 4 blocks makes one module, so that when top and bottom block hold two middle blocks, it complete as a one structural module by the jamming phenomenon. Once that module is completed, that module can be repeated to be aggregated to any shapes. Of course, we can do easy simulation. I mean, in this case, controlling two different angles based on the 3D printed dowels or dowel geometry can allow that angles, or the block itself can allow that the angle change. So based on this control, we can limit the number of modules, but we can also achieve the certain desired overall form. So at this point, the block design, top side, bottom side, is the stacking phase, so that which needs complete accuracy for the accurate jamming phenomenon. On the other hand, right and left side is opened as after the firing process, the inaccuracy is okay. It's only for the controlling the porosity of the overall stacking system, so that we can simulate that how the limited module can evolve into different geometries by the digital simulation. So in order to do this, we know that the brittleness of the material should be our friend, not the enemy, because we want to dance with this situation. So that we received the generic data from the Boston Valley. I mean, we applied the safety factors for our experiment. However, we focus on this rupture modulus, so that's the point where the brittleness happens with 30 megapascal. So that our engineering team provided us valuable information. So that right before we reach the rupture point, so that we can apply about 60 kilogram force for this 4-block module. So that, in another word, one block can hold about 130-pound weight coming from the top, including the weight of these blocks. So that what we learned, I mean, as expected, the most stressed area is that the jamming areas, but the failure happens in the dowel first, and then the area in the leg around the jamming area. So that's the interesting learning. So the leg flexure stress in the leg is not a problem, but the brittleness of the jamming is an issue for our block design. So that we tested with the ABS dowel. So the ABS just represent the plastic materiality. So that it is very hard, but it doesn't fail, but it has a minor, very small elasticity in the nature of the material. So that if we do this, it functions as distributing the stress area in the jamming area, so that it can take more load, so that it can increase 30% the load capacity. In return, compared to the previous dowel, which is a hard dowel, for example, the terracotta dowel or steel dowels, those only makes 3 millimeter displacement overall 1 meter our test module. So that now if we use the plastic dowel, it increased 30% load capacity, but it gives twice more displacement. So 7 millimeter over 1 meter. So that's the very promising study, because we can innovate that design of the jamming, and also, so this is another test that including the gravity of the weight, and also we push the from the side, a wind load, or someone is pushing from the side. We learned that same amount of force, about 60 kilogram force, will reach the rupture point, so that the one block can hold about 30 blocks on top of it before the failure. So we are very comfortable to simulate this type of cantilevered arc using the terracotta blocks. For this case, we tested with just mock-up plastic blocks. So for the terracotta fabrication, we decide to try this image on the left, just to proceed with the potential application for the building envelope and the building facade simulation. So I will, so Sean Murray can continue the fabrication part.
Yeah, so the fabrication I think is where our team bonded and learned the most through the project. The next 3 slides are a bit of sort of background. The first one there was AU students building and designing kilns with me through a course. And this slide is an example of some artwork and research that I'm doing in the studio. This is an example of Jonathan Hopp's artwork and research. He's an assistant professor, and throughout the summer, he fabricated a series of ceramic stools that utilize the ceramic 3D printer. So UB printed out our positive shapes of our X block unit. And we decided to use this solid hourglass shape. So essentially we filled in the space between the appendages of the X. And in doing this, we decided that it was important to try to get the unit to be as flat and as planar as possible through the drawing and the firing process. We then fabricated 6 press molds at Alfred. This is a quick video clip of us sort of going through the process of making the unit. Compressing the Boston Valley clay into the press mold. Ideally, in the factory, we would be using a ram press application. The ram press would allow us to make the units very quickly, and it would also sort of help with uniformity as far as compression with the materials. But at Alfred, we kind of went with what we had available and what we knew. This is our group in Alfred applying the surface to our dried units. From here, the units are now loaded into the kilns at Alfred. Should be next slide. We used a traditional terra sigillata surface. You can go back to the next one or the previous one. Yeah, so with the surface, we used a traditional terra sigillata, which is the fine particles of clay. And in liquid form, we added ceramic pigment and heavy metal oxides to create the palette. And in the end, we had a really beautiful sort of silky matte clay surface. And I'll turn it over to Dan.
Thanks, Sean. So once the units came back to UB, we were working on trying to get back some of the tolerance and precision that's usually lost throughout the kiln firing. So what we ended up doing was taking these pieces to the water jet, and we didn't want to water jet out the entire piece because we were trying to keep some of the integrity of the original formed pieces that were done at Alfred. But we also wanted to register the post machining through parts of the material that exposed the raw clay body, and then the sort of unglazed parts that were the post process parts. So we created a jig that allowed us to clamp in the small, medium, and large pieces into the water jet. You can see the machine spinning around. What that was doing was redistributing the kerf of the water jet out to the scrap parts of the material so that we could maintain a perfectly vertical edge through all of the pieces that we had. And this was really important for the assembly process. We were working on both the top and the bottom of the units at the same time so that we made sure we had a precise relationship between the top legs and the bottom legs of each unit. So this slide shows how the final pieces came out. So I think one thing that we were really, really happy with was how the water jet interacts with the glaze. So some of these pieces are shown from the front and some of them are shown from the back. And we were really interested in the sort of crisp edge that was able to be created through between the glaze and the raw water jet cut edge. So we held a pre-workshop at UB's Smart Fabrication Factory, and you can see most of our team there. We worked on our first sort of trial assembly of the units, and we were able to achieve 2 cantilevered surfaces that were attached on temporary bases. And I think one thing that we were really impressed with, Jane, you can move to the next slide. I think one thing that we were really impressed with was the general rigidity of the overall structure and the ability to actually assemble that without any armature or scaffolding underneath. So here's a quick time lapse of our assembly process. Some important things to note here, basically a single person assembly. So one person was able to do most of it. Once we got to the top, it was useful to have two hands, but not totally necessary. Ground up construction, so we were able to start at the base, not use any kind of scaffolding, and complete the piece. And the pieces were actually able to cantilever while we were going through that assembly. So the final prototype here, with a figure behind, stands about 4 feet tall off the base and is made of 39 units. So there's curvature created in both directions, a cantilever coming off in the left image, and then the double curvature to the right image. And this is created using only 3 unique units, all of which are planar units. And then the ABS plastic inserts allow us to control the growth direction of the piece, as well as the sequencing of the small, medium, and large pieces. So on the right image, you can see the sort of T-shaped insert pieces and then the dowels that sort of jam the pieces together. And then in the next slide, we'll get an even better view of those dowels. So you can see that the tight connection is created actually between terracotta and ABS plastic. This removes any terracotta to terracotta connection. So moving forward, one thing that we're interested in was actually reducing the amount of pieces from 3 unique pieces to 1. So in this scenario, we actually only have 1 piece, and then all of the geometric changes and sort of flexibility in the system is created in those end inserts. And we're also working on removing the dowel from the middle to get rid of that structural connection and relying on gravity for the system instead. And then another sort of test that we're working on side by side with this is with Jonathan Hopp at Alfred. We're working on 3D printing the units. We think there's a lot of potential here to customize the units further, reduce the amount of waste without the use of molds. And we can closer approximate the units. We can potentially redistribute some of the material to work better with the water jet cut edges while being able to remove material in areas that aren't being water jet cut to expose more of that raw versus glazed scenario that we're looking at. So here you can see the texture created by the 3D printing in contrast with the really smooth edge that's created by the water jet cutter.
So we are interested in the next step of kind of study, that how we can utilize this reconfigurability. So that this is one example that that this can be used for the low-tech dynamic facade, so that it can be used for the shading surfaces for the summer season, so that it can block the heat gain, and then which can be reconfigured into inside, so the inside of the curtain wall, so that it can be the thermal mask, so that functioning as a kind of mobile trauma wall concept. So also when it is reconfigured for the next season, because of our blocks are kind of organized into different ways, so that the overall pattern of the colors will be different. This idea of the mobile kind of a thermal mass can be also used for the residents, just to increase the energy performance. This is in the study we're interested in, and then we hope that we can develop and research further to be presented in the future. Thank you very much. And then again, this is a fantastic event. We are very happy to be part of it. And then our students contribute a lot for all the studies. So thank you very much, everyone.
Thank you very much to UB and Alfred. It's a lovely project, and there's some interesting questions. I think a lot is about the relationship between these 2 mechanisms of printing, as 3D printing, and then also extraction and cutting using the water jet. There's a question about the 3D printer product can then be machined after the fact with the water jet. I think there's some really beautiful results as that is beginning to happen. As you're thinking of this precision, could you speak a little bit to just the relationship between, like, the design and actually the machines that you're now moving and using? Is there a certain kind of understanding? I'm just thinking of scale and other things. Obviously, you're representing it as on a building scale, but as you think about these machines, can they move into a kind of an industrial production?
Yeah, I mean, I think a lot of the initial studies actually went into reducing the amount of water jet time to try to think about how that machine could potentially scale up. We were looking at about 7 minutes of cutting per unit, down from about 15 to 20 minutes a unit for cutting out a full unit. So I think a lot of the focus on the project has been, how do we get back the tolerance while reducing the amount of time that it's spending on a generally really slow machine? So how do we use what the water jet is really good at, which is making these really clean edges between raw and glazed, cutting sort of perfectly vertical and giving us the really tight tolerances. So I think it could be further refined. I think with a method like ram pressing, where we could get a really consistent unit out of the ram press and have a little bit more maybe predictability on how that would work in the kiln. And then really getting into how do we only machine those areas that absolutely need to be. And that was, I think, one of the parts that the moving forward steps where we're trying to get rid of that dowel and really focus on where that high precision, high tolerance connection is happening, so that we can reduce the amount of time. So I think that was definitely something that we were conscious of, was just trying to move towards scalability and the use of the machine. The great thing about the water jet is being able to cut all of these varieties of different materials. So we can cut clay, we can cut metal, we can cut glass, basically anything. So it's one machine that we can use to get these cuts that we're looking at in a project like this.
Great, thank you so much, guys. It's a beautiful project, and we look forward to your continued participation in ACAW.